हेलो दोस्तों, मेरा नाम प्रियांक है। मेरा एक प्रोजेक्ट था बीटेक में, व्हीकल राउटिंग प्रॉब्लम विद टाइम विंडोज। सो आई वर्कड ऑन दिस प्रॉब्लम स्टेटमेंट इन माय बीटेक फाइनल ईयर project alongside with my project partner Pooja. So what is vehicle routing problem with time windows? So let's first understand what is vehicle routing problem. It is a simple variation of traveling salesman problem, we can say, which we are trying to solve with genetic algorithm. We are here using multi-objective genetic algorithm, MOGA, we can say in short. So here we have two requirements. We have to serve some customers who have some time-bound windows where in which we have to serve them. We have to use, our objective is to use minimum number of vehicles which travel minimum distance, so we can save the fuel cost also. So we have two objectives. We have to minimize the number of vehicles, and we also have to minimize the distance traveled by them. So we had to select the routes optimally so that these two objectives can be minimized at once. So here we can represent our problem pictorially. So depot is the number of zero, and other numbers like 1, 2, 5, 7, 3, 4, 9, 6 are the customers which we are going to serve. So we can serve our customers in many ways, like 251, or we can go by 2, 7, 3, 4. Multiple routes are possible, but we have to select the routes optimally so we can minimize the number of vehicles and minimize the distance also. So this is an example. There can be three routes served by three vehicles which can serve our objective optimally. So we are using multi-objective genetic algorithm. The genetic algorithm have a defined flow, like we first initially generate a population, then we select some parents from them, we apply crossovers, mutations, and then a new bigger population generated. We select some fittest from them and eliminate some population which is not fit for our selection, and we apply the crossover and mutations again and again iteratively for number of generations. We can stop at some point of number of generations, like when our solution is not improving much with number of generations increasing, we can stop and we can get some optimal solution with that. So genetic algorithm works in a way like that. You already if you are working on vehicle routing problem, you already have the knowledge of this if you are using of genetic algorithm. So we can represent our set of customers like a chromosome, where 241, these are called genes. They are individual customers, and we have to arrange them in an order so that we can form some routes from them which can serve our objective optimally. So this can be a set of route, like we can go from 2 to 4 to 1 to 6 to 3 to 5, so that our distance is minimized and number of vehicles are also reduced. So we in genetic algorithm we have specifically two operators, crossover and mutations. We have multiple type of mutations and crossovers, like partially mapped crossover and cyclic crossovers. So we are not going to talk about that. We have implemented these also in our code. We have actually coded this project in C++. So I will not be talking about these in all. So what is our main focus is BCRC, best cost route crossover. So this crossover was specifically designed for this problem statement, vehicle routing problem with time window. Ombuki designed this algorithm, and it gives best optimal results. BCRC can be seen here, like we first select two parents from to whom we are going to apply the crossover operator, and we select a segment from of customers from one parent and in both parents, and like we have selected 5 6 the customer segment from the parent 1 and 7 and 3 from the parent 2. Now we delete the 5 6 customers from the parent 2 and we delete the 7 and 3 customers from the parent 1. Now we have, since we have deleted the 7 and 3 from the parent 1, we have to insert them also, because our we have to serve all customers, we cannot leave any other customers. So what we will be trying is, like we will be selecting one like 3 and we will be inserting it at every possible position in the route, and we will be seeing which is the best optimal position for it, and then we will also insert 7 like in the same fashion we will insert it at every possible place and see which is the best possible place for it. So it will generate a child c1, and same will be same operation will be repeated for the parent 2 also. 5 6 have to be inserted, so we first insert 5 at the best possible position, and then we insert 6 at the best possible position, and we generate c2 also. So c1 and c2 maybe, not surely, but maybe have better performance in terms of optimality of number of vehicles and number or distance covered by the vehicles. So this crossover gives us some better results generally, not all time but generally. C1 and C2 are better in terms of performance from their parents. We have also, we know we are going to use mutation also. We have tried different type of mutations like swap mutation, cyclic mutation, inversion mutation. We will not talk about this in this video. You can generally search it on internet. There are multiple options available. So we have coded this project in C++, and we have coded the BCRC also, which was not available anywhere on the internet. Algorithm was available, but implementation was not available, and it was hard to implement. So we have implemented it in C++, me and Pooja, and we have got comparable results with what are the benchmarks available online on internet. Like, we have, in some cases we have got some better results also, which we have marked with bold, and in some cases we have got exact results, in some cases we have got similar results. So our code is perfectly working with BCRC, what was intended by MOGA. And I will be showing you the code also, C++ code. So this is the C++ code. It's quite heavy actually, and I will go through this once. So we have made a class of customers here, and we have defined some number of customers, number of chromosomes. Alpha beta are the parameters which we'll be using to give priority, which, like, we are prioritizing the number of vehicles or number of uh, total distance covered by, because this is a multi-objective genetic algorithm. So we have to give importance to one of the, at least one of the, some importance to one of the objectives, which can be given more of preference. So alpha beta will be doing this job. We have defined a class of cost which we will calculate for a given route, like how much distance it is traveling, how many number of routes are there, how many number of vehicles being used. We will be taking inputs which are available from Solomon's benchmark. I will upload the inputs and outputs, all these files on the GitHub, and give you all the link in the description of the GitHub profile. Uh, we are using Pareto ranking procedure to get which are the fittest of the individuals, fittest chromosomes available, to select and eliminate the non-fit uh, individuals when we are going through iterations of number of generation and generation, generating new populations and eliminating some old population. Cost function is also there to calculate the cost of a given chromosome, like how much cost, how many number of vehicles it is using, and how much distance it is going to take. We have used different type of mutations also, like inversion mutation, swap mutation, cyclic mutations. So mutation functions, one by one, can call all of them. I've used the inversion mutation here and commented out all two. And here we are using the BCRC. Here we have implemented the BCRC crossover with two functions. It was quite difficult to implement because there was no implementation available on internet in any language. I searched it out. Algorithm was available given by Muki, but not the exact algorithm. It was just given the method. So we have developed our own algorithm also. We have implemented some other crossovers also, so we can compare with this, like BMX crossover, cyclic crossover, but these crossover will not work in this problem statement. VCRC is the best crossover for this problem statement because it was intendedly developed for this problem statement. So crossover functions one by one can call these populations, call these crossovers and insert the get new children and insert in the population. And one by one, what we will be doing, we will be applying, like we can we will be applying some fitness function like Pareto ranking procedure, and we will be eliminating some non-fit population, and we will be selecting some best fit population. So this will give us some better results when we run this algorithm generation by generation. So we can like run different number of generations like 300, 400, but this algorithm like this code is too complex, BCRC is too complex, time complexity is too high, so it takes a lot of time. Like I have run this algorithm on real for 300 generations, and it took 283 seconds to implement. We can see the outputs like number of best number of vehicles 10, average number of vehicles 10, because in genetic algorithm we get multiple different solutions, not a single solution. So we have to select which one is best for us. Like here the best chromosome which have best distance and best vehicle is this. We have uh, made routes from this also, so we can test if our results are correct or not. We have tested it, it is correct. We have compared it with global results, and because it was our BTech final year project, so we have to be sure for everything. You can also implement this, get this code in my GitHub profile. I will give link in the description. You can implement it uh, your own. First try to run for some smaller number of generations, because it take a lot of time, so you might lose the patience and say like code is not working. So first try to run for 10 generation, 5 generations, and then increase the number of generations for your convenience. It can go up to any number of generation, but it takes a lot of time because genetic algorithm in itself is very complex. BCRC is in itself very complex. If you can modify the code and get some better time complexity, please let me know also. I will also try to improve it. You can get all the inputs, outputs, files. You can get the PPT also, which I will be sharing in the GitHub profile, so that you can get some knowledge. For this project, we used OMBookie's research paper. You can get it simply by searching vehicle loading problem with time window, OMBookie results on internet. I will try to get the PDF and put it in my GitHub profile. Thank you all for watching it. Thank you.